right, away we go. All right, well, I think we'll just put the periodic table up there for some inspiration. And to start us off, we have our little 2-page practice sheet. And so let's just take a look at that. And if we go to our little chart, all right, the first element that we have there is molybdenum. So what is the symbol for it? MO. Right there it is, element number 42. All right, now how many protons does it have? 42. Right, because the atomic number, remember, tells you that. What else does the atomic number tell you besides how many total electrons? That's right. Now, how many valence electrons would you predict for this thing? Well, what group is it in? 6. All right, there you go. All right, now remember, valence electrons are just those in the highest energy shell. All right, how would you classify it? Is it a representative element, a transition element, or a noble gas? Well, it's right here in the middle of the table. What do we call those? Transition elements, right. Now, how would you classify it according to being a metal, a metalloid, or a non-metal? It's a metal, right. Because remember, over here we have that dark zigzagging line. If you get to the left of it, they're metals. If you go to the right, they're non-metals. The ones that are right on the line are the metalloids. All right, so if we go to lead, lead is what symbol? Pb, and it's right over here. Element number 82, so how many protons does it have? 82. How many valence electrons does it have? No, valence electrons, what group is it in? It's in group 4, so how many valence electrons does it have? 4. All right, how would you classify it according to being representative, transition, or noble gas? Representative, right, because the ones over here, like from 3A on over, those are representative except the noble gases, which are the last one, group A. All right, and so how would we classify it according to metal, non-metal, metalloid? It's a metal. All right, very much so. All right, here we are. All right, xenon, which is right over here, number 54. So how many protons? 54. Wow, how many valence electrons does it have? 8. Now, what's the only exception to that 8 for elements that are in group 8A? Helium. How many does it have? Just 2, right. How would you classify xenon then according to the representative transition noble gas business? It's a noble gas, and with respect to metal, non-metal, metalloid, it's a non-metal, right. And selenium, all right, let's see where we have that one. It's right over here, number 34. So how would we go with that one? What's the symbol for it? Se, all right, how many protons does it have? 34. And valence electrons, it's in group 6, so it would have how many? 6. And how would you classify it then on the representative transition noble gas business? It's representative, right. All right, and metal, non-metal, metalloid. Well, non-metal, but it could be classified as a metalloid as well. That one's a little tricky, all right. Now, either one would work. Now let's write the formula, unit formula for the following compounds. So let's blank out the periodic table. And so the first one is barium carbonate. Who wants to come up and write that formula on the board for us? Oh, don't be bashful. Come on, somebody. Excellent volunteer. There we go. Make it nice and big. All right, barium carbonate. Now make sure that's a capital I. Don't you use your rating. That's it. Uppercase O. Because remember now, what is carbon? No, you handed it on to somebody else. What is carbon? It's carbon and oxygen. So there we go. Barium, what's the charge on the barium ion? Plus 2, what's the charge on the carbonate? -2, so it just takes one of each. Okay, so the next one up is iron 2 sulfide. All right, that should be an easy one. Excellent. Hand the marker to somebody else. Get somebody on the other side of the room. There you go. Excellent. All right, now, what is the charge on this iron 2?
2.
Plus 2, and the sulfide is -2, so it just takes one of each, and there it is, it's done. All right, now the next two,
You don't have to write iron 2, like the Roman numeral.
No, not, well, only when you're naming it,
Okay.
okay, but not in the formula. Because the iron 2 ion is just Fe plus 2, okay? All right, next one we have to give the name. So this one is, and I'll go ahead and write the formula up here. All right, CuNO3, so come up and write the name. All right, copper 1 nitrate, that's exactly what it is. Because the nitrate we know is a -1, so there's only one copper, it's got to be a +1, therefore it is copper 1 nitrate. Okay, the next one we have, this is a loaded one. Okay, so come on down and pop the name up there. All right, right, ammonium acetate, that's it, okay. And there we go, I'll write the rest. All right, very good. Okay, so, any question about that? Ammonium is the NH4, and then the C2H3O2 is the acetate. Just one of each, so that's all we got to do. And this is +1, this is -1 on the charge, and that's it. All right, now, the next one says if we put together the elements cobalt and sulfur, would we form a compound A that is either ionic or covalent? And then part B, explain. All right, now, what do you think? Well, if we, let me just pop the periodic table back up here. All right, cobalt is here. All right, and sulfur is, of course, here, let's bring it down so it shows up a little better. There's cobalt and there's sulfur. All right, so cobalt's a metal, right? Sulfur's a non-metal. What kind of a compound do you typically get when you put together a metal and a non-metal? Ionic, exactly. That's right. What kind of elements do you typically put together if you have a covalent compound? What were those? What kind of elements were involved in those? Well, suppose we had carbon dioxide. Remember, that's covalent. There's carbon, there's oxygen. How would you classify those elements? Are they metals or non-metals? Non-metals. Aha! So if it's a metal and a non-metal, it's probably going to be ionic. They're going to form ions. If you're putting together non-metals, you're probably forming a covalent compound. In fact, some people, when you go to the cocktail party in one corner of the room and they're chattering away, they're all called covalent compounds, non-metal compounds. They sometimes use those terms interchangeably. All right, so there you go. So, really, the reason why it is ionic is because we're putting together a metal and a non-metal. And that usually gives you an ionic compound. Oh, it's pretty simple, isn't it? Yes. All right, well, let's take a look at the next one. Now, there we're given a... God, throat burn, some gloves. All right. All right, now, here here we're given the Lewis formula. Alright, so now, there it is. Now for A, we need to draw the structural formula. Oh, I feel like somebody needs to come out and do that. Who wants to come and draw the structural formula for us? Oh, that's cake. I've already done the hard work for you. Here, come on. Now, how do you turn a Lewis formula into a structural formula? What do you do? Structural formulas, remember, use the lines to represent what? The shared pairs of electrons. All right, that's a gold star. All right, very good. All right, now we want to know the shape. Now again, if we go back to the electron dot formula and apply the rules that we know, that should be very easy to figure out. So first of all, how many atoms are in this thing? 3. And what about the unshared pairs of electrons? Are there any on the central atom, yes or no? No. So if it's a 3-atom molecule, no unshared pairs on the central atom, what is the shape? Linear. Right. Now, let's talk about the next one, which is telling us whether it's polar or nonpolar. So for that, we need our dipole notations. Now, which of those two elements would you guess has the higher electronegativity? The carbon or the sulfur? I don't know about that. Here, let's put the screen back down and put the periodic table back up. All right, now, what's the trend? Well, there's not going to be a lot of difference, but typically if you go off toward the right, they tend to increase, remember. And if you go to the left, they tend to get smaller. So the sulfur is probably a little bit higher. All right? Okay. Now, if that's the case, where are we going to put the dipoles? Well, looks like we'll have one there, and looks like we'll have one there. Now, what would you say about that? Is it going to be polar or non-polar? Non-polar. Why?
Because they're both pulling out.
Right, they're pulling out at 180 degrees apart. They cancel out. There's no net movement, so it's a non-polar molecule. That's exactly what it would be. All right, well, that's simple, isn't it? Now, if you had something like that on your test next Wednesday, you ought to be able to answer that, shouldn't you? Well, I should think. All right. Well, let's see. I think we had gotten into that wrinkle on solubility the last time, hadn't we? So let's go back to that, and I have a little something to give you that might help out a bit with this. And so, let's just kind of bring that slide up, and come
On this handout,
on.
for number 5, you have carbon disulfide, but then B and C is sulfur dioxide.
Oh, forgive me. No, mine says sulfur dioxide. Maybe there was an older version of that that had another compound on it or something.
Okay.
Okay. I think I updated it, so you might check. There may be another version.
Okay.
But anyway, no, it should say sulfur dioxide. No. Yes, sulfur dioxide. Carbon disulfide is what it says. All right. Well, actually, I think I want the thing down. All right. Here is a little handout. Now, I put this on the web page, but I went ahead and made copies because you may not have noticed it was there. So just kind of, pass them around. Put half of them here, and then I need the extras back. And this is dealing with the formation of solutions. Now, remember when we are talking about forming solutions, we have a little old expression of likes dissolve likes. And in the sense that they have to form like interparticle forces. Alright, so if things can form some kind of like or similar interparticle forces, they'll probably go in solution, and if they can't, they won't. Alright, so with that thought in mind, remember the interparticle forces, what they are. We had ionic ionic bonds, and so what kind of substances do those apply to? Ionic compounds, right. And then we had things like hydrogen bonds and dipole forces. Well, those apply to what kind of substances? Well, how about polar covalent molecules, right? Okay. And then what was the other one? We had dispersion forces. What kind of substances do those apply to? Non-polar, right, absolutely. Alright, so now let's just take a look at a few little examples, and we'll go with some generalities, and we'll look at some specifics. So, let's see, here we go. Alright, so we've already said the likes dissolve likes. And we know what a solution is. It's a mix of solvent and solute. Solvent is the dissolving medium. The solute is the substance that's dissolved. So if you're making up a sodium chloride solution in water, an aqueous sodium chloride solution, what is serving as the solvent? What's the dissolving medium in that case? Water, absolutely. And what is the solute that's being dissolved? Huh? Sodium chloride, an aqueous sodium chloride solution. The solvent is water, and the solute is sodium chloride. That's right. Okay. Alright, so what happens if we put together two polar compounds, a polar solvent and a polar solute? Well, now, let's think of them independently first. Alright, let's suppose we have something like sucrose, good old table sugar. Alright, it can hydrogen bond with itself, and it does, because what is the physical state of sucrose at room temperature? It's a solid. So it obviously has pretty strong interparticle forces between the molecules. Well, they're going to turn out to be hydrogen bonds. Alright? Now, let's think of water. We want to make an aqueous solution of sucrose. Alright, what kinds of interparticle forces do you find between closely spaced adjacent water molecules? Hydrogen bonds, absolutely. Alright. Now, if we mix those two things together, if we mix the sucrose with the water, what is going to happen between the two? What's going to happen? The sucrose is going to hydrogen bond with the water. And what's going to happen as a result of the sucrose hydrogen bonding with the water? It's going to dissolve. It's going to disperse throughout the water, and you've got a solution, you've got a homogeneous mixture of sucrose and water. Alright? Now, pretty simple, isn't it? Alright, so there you go. So if you put together two polar substances, a polar solvent, a polar solute, you're likely to get a solution. Why? Because they can form either hydrogen bond or dipole forces with each other. Alright? Similar interparticle forces. Alright? Very simple. And you'll note there on the sheet, what does it say if you put together a polar covalent solute and polar covalent solvent? Alright? You get a solution bond, because they hydrogen bond or they form dipole forces with each other. Right? Alright? Now that's pretty simple, isn't it? Now don't you think you can memorize that? Better, because I'm sure you're going to have a solution problem on the test. Alright? Well, let's kick it up a notch. Alright, now this is the fun one. And that is where we get to the polar solvent and the ionic solute. Now Now let's come up with an example of that. And let's take one first of all that we know is going to form a solution. And to that, let's just kind of digress a moment, and let's do some drawing up here on the board. And let's suppose that I want to make an aqueous sodium chloride solution. All right. So what is the solvent going to be? We just said that a moment ago. Water, right? All right. And what is the solute? Sodium chloride, is it not? All right? Because that's what we're going to dissolve in the water. Now, as we know, water is a polar covalent compound, right? And it's capable of hydrogen bonding with itself, right? That's why you find water in the liquid state. It's got a lot of hydrogen bonds, which are reasonably strong. All right, it also has poles, does it not? It's a polar molecule. Which end of the water molecule has the partial negative charge associated with it? Which end? Huh? You don't have that in your notes. Which end of the water molecule has the partial negative charge? No. The oxygen. Why? All right, now remember, there it is. Oxygen has the higher electronegativity, right? And this is a nonlinear or bent-shaped molecule. So we put the dipoles up there because of the bent shape. They reinforce each other. So the oxygen end is the one that has the partial negative charge. The hydrogen ends both have the partial positive charge. All right, remember that. All right, now, there we go. What kind of interparticle forces have you got here? Well, sodium chloride's what kind of compound? First of all, what is it? Ionic or covalent? It's ionic, isn't it? All right, now, what kind of interparticle forces are you going to have there? What are you going to have between the sodiums and the chlorides? Ionic bonds, I do believe. Do you not? Okay? All right. What is the charge on that sodium ion? That'd make a nice question for next Wednesday, wouldn't it? I think it's +1, isn't it? What's the chloride ion charge? -1. What's an ionic bond? How would you describe it? How would you define it? What is it? Attraction between what two things? Huh?
Two different elements?
Well, not necessarily elements, no. Elements, if you're talking about elements, atoms are neutral. Different charge what? Ions, right? Sodium's a cation, chloride's an anion, right? Force of attraction between cations and anions. That's an ionic bond, is it not? All right, now, so here we've got ionic bonds, and there we've got hydrogen bonds between closely spaced adjacent waters. Well, what is a hydrogen bond? Let's just quickly refresh our memory on that. What is it? Attraction between what two things? Huh? No. Suppose I put another water molecule right down here. Where's the hydrogen bond going to go? It's going to go between the hydrogen on that molecule and that unshared pair of electrons on that oxygen, right? Hydrogen bonds are attractions between hydrogens and an unshared pair of electrons. Did you all forget things over the weekend? Chance? I hope not. All right, now. All right. Now, we've got a little there for inspiration, so now let's come back and take a look at this. All right, let's just put up here, let's say a little sodium chloride crystal. So there's a sodium ion, there's a chloride, and we'll throw in another sodium, and put another chloride here, and so on down the line, and they kind of alternate. All right. Alright, so that's enough to get us started. Now remember now, at room temperature, that sodium chloride is a solid, is it not? I mean, sodium chloride is table salt. So, you know, unless you've got really humid conditions, what do you find in your salt shaker? A solid, crystalline solid, right? Okay. Alright, now, let's throw some water in here. And I think I'll switch to green for that, just for kicks. Should use blue, but my blue marker's about dead. Alright, now, water. Remember, as we've said, the oxygen end has a partial negative charge, does it not? The hydrogen end has a partial positive charge, or pole. Now, which end of that water molecule is likely to be attracted to the sodium ions that are right here on the surface of this crystal? Which one? The oxygen end, absolutely. So anywhere I have a sodium exposed, I'll bet I'm going to find a water molecule coming along and aligning with it, something like that. Now, we've got a force of attraction here, obviously, between the two. And that force of attraction that we have between the ion and a pole on a polar molecule is called an ion dipole force. All right, once again, what is an ion dipole force? Force of attraction between what two things? You guys remember we talk about these things, it's always between two things, right? Between what two things this time? An ion and what else? The opposite pole of a polar molecule, right? It's the force of attraction between an ion, and the opposite pole of a polar molecule. Well, a sodium ion has a charge of what? +1. So which pole of the water molecule has the opposite charge? The oxygen end, right? That's the one that's negative, partially negative. So it's attracted to the sodium ions. Now, I'll bet with that thought in mind, you could not guess in a million years, if you had that long, which pole of the water molecule is going to be attracted to those chloride ions? The hydrogen, right. So water's going to come along and it's going to align something like this, wherever you find an exposed chloride ion. And we have ion dipole forces forming there. Now, on the surface, we've got these ion dipole forces forming with the ions. Now, as more and more ion dipole forces form, guess what's going to happen to the strength of the ionic bonds that have been holding those ions together? They're going to weaken. That's exactly right. So as you form more and more of these ion dipole forces on the surface, the ionic bonds between the ions start to get weaker. Now, what happens to particles? What happens to the distance between particles when you start to weaken their interparticle forces? Do they get closer together, or do they move further apart? They start to move further apart. That's right. So as, let's say, a sodium starts to get a little far afield, I'll take that, whoops, black, that had a shame on me. All right, let's say that one's getting a little far afield. What's going to happen now with the waters? Well, they're going to start surrounding it. They're going to be able to move in here and get around it from all angles. And guess what's going to happen when you totally surround the sodium ion with water molecules? Now water's gone? Free, exactly. It's going to fly the coop. it's going to come out here. All right? And it's going to be completely surrounded by water molecules. And it's now going to be what we would call a hydrated ion. All right? Hydrated ions, totally surrounded by water. Where are they going? Are they going to stay in a crystal? No. They're going to disperse throughout the water. And when all of your ions have dispersed throughout that water, what have you got? You've got a solution, don't you? Okay? Now, isn't that neat? Isn't that simple? Yes! All right, you put that solid, ionic solid in with the water. The water molecules start to align with the crystals on the surface, with the ions on the surface, forming those ion dipole forces. All right? Those ion dipole forces dampen the ionic bonds. The ions start to move farther apart. More water molecules move in and surround them, giving us hydrated ions, and hydrated ions disperse throughout the water, and you got a solution. Now, what is difficult about that? Well, not much of anything. All right, let's just take a look at a fancier, long version of that. All right, so let's just go back to the slides for a moment. And here we go. Well, we've talked about all this stuff, where the water comes in, forming the ion dipole forces, dampening out the ionic bonds. The ions move further apart. The water comes in and surrounds it. You have hydrated ions. You have a solution. All right, now here is a little fancier version. There's the solid crystal with the sodium chloride ions down in the water. Water comes associated particularly with the surface ones first, and they start to separate as we dampen the ionic bonds, and then finally we end up with these hydrated ions in solution. There they are, surrounded completely by water molecules. Now, what would happen if you took this salt solution, this aqueous solution of sodium chloride, put a little old burner down here and started heating that and boiled off the water? What would happen? What would be left? Huh?
The salt would stick there.
Right, it would. You know, you go right back to solid sodium chloride. That's right. Pretty simple, isn't it? Isn't it? All right. Now, we know that forms a solution. But here's the trick when it comes to ionic compounds. Not all of them go readily into aqueous solution. All right? So let's take a look quickly at something that doesn't and see what is the difference. All right, now I'm going to leave my water molecules. But this time, rather than putting out sodium chloride, we're going to take a look at something called silver chloride. Now, silver chloride is not very soluble in water. In fact, we would say for all intents and purposes, it's insoluble. All right? Now, what is it? Well, again, we have the silver cation this time. It's +1. And there are the chloride ions. All right, so we'll throw some more silvers in, some more chlorides, and so on down the line. All right, now, why does this not form a solution with water? Well, do we get the usual ion dipole forces forming? Yes, we do. But here's the deal. Yes, we'll get ion dipole forces here on the surface, just like we got before. And of course, since the silver is +1, it attracts the negative pole to water. And since the chloride is a -1, it's going to attract, obviously, the positive pole of the water, which is the hydrogen. So we get ion dipole forces. And the ion dipole forces attempt to dampen the ionic bonds. But here's the deal. This time, the ionic bonds are stronger than the ion dipole forces. So what happens? Nothing. You get very few ions going off as hydrated ions. You don't get appreciable numbers of hydrated ions this time. time because the ionic bonds have the upper hand. Here, the ionic bonds are stronger than the ion dipole forces. All right, so what's the difference? What's the difference between an ionic solute that does go in solution and one that doesn't? The strength of the ionic bonds. That's it. You get a solution if what happens? What does it say there on your sheet?
If the dipole forces are stronger.
Right. If the ion dipole forces are stronger than the ionic bonds, you get a solution. What happens if the ionic bonds are stronger than the ion dipole forces? You don't get a solution. Now, how do you want to know whether it forms a solution or not? Don't worry, I'll tell you. All you got to do is explain. Tell me either why it does or it doesn't. You know, there are rules on solubility for ionic compounds. We're not going to get into that, so don't worry. I'll tell you whether it's soluble or not. You see, I'm meeting you halfway. I'll tell you that. All you got to do is tell me why. Right there on the sheet, isn't it? Cake. All right? There you go. Now, let's kick it up a notch. And let's take a look at what happens if we put together a nonpolar solvent and a nonpolar solute. All right? Now, here's something that is definitely a nonpolar solvent, and that is the solvent toluene. Toluene is nonpolar. All right? Now, if it's nonpolar, what kind of interparticle forces are you going to have between closely spaced adjacent molecules? Dispersion forces, right? And toluene is a liquid at room temperature, so it's got reasonably strong dispersion forces holding the molecules together. All right, now let's take for our, this is our solvent, we'll say. For our solute, let's just use plain old cooking oil. Now, we know that oil is nonpolar as well. All right? And so what kind of interparticle forces are you going to have between adjacent oil molecules? Remember, it's a liquid at room temperature. Obviously, it's got some kind of reasonably strong interparticle forces. What kind of interparticle forces apply to nonpolar covalent compounds? Dispersion forces, that's right. Now, if I mix those two things together, what do you place your bets? Are we going to get a solution or not?
No.
No! Why not?
They can't mix.
Ah, but they do. Yes, it forms a solution. Why? They can form dispersion forces with each other, can't they? I should think they could. All right. So if we put together a nonpolar solvent and a nonpolar solute, yes, we ought to get a solution. Why? Because they're forming dispersion forces with each other. Lights dissolve lights. Remember that. All right? So, we've got dispersion forces here in toluene by itself. We've got dispersion forces between oil molecules. When it's oil by itself, you pour them together and dispersion forces form between the two, you're going to get a solution. And you do. All right? Drop the oil down the toluene, give it a shake, and you've got a solution. Now, that's pretty simple, isn't it? Well, what about something like paraffin wax, which is a solid at room temperature and is also nonpolar? What kind of interparticle forces would you have between adjacent molecules in that case? Well, if it's nonpolar, what are they going to be? Dispersion forces. All right, what are your bets? If you put that with toluene, give it a shake, you going to get a solution? Yes, you will, indeed. All right. Now, let's up the ante a bit. This time, I'm going to switch from oil to sucrose. Now, let's go back. We've already said what kind of a compound is sucrose. What is it? Polar, isn't it? Alright, so what kind of interparticle forces apply here between adjacent sucrose molecules? What kind? Well, you got it there in your notes. We already talked about it today. What is it? What kind of interparticle forces apply here? No, not with a polar covalent compound. That would be true over here. I can go ahead and write dispersion down for toluene. We already had it there. I think it's going to be like hydrogen bonds, don't you? I think we already mentioned that. Now, if I take a tube of liquid toluene and I sprinkle in some solid sucrose and I start shaking away, am I going to get a solution this time? I am not. Why not? Why does a solution fail to form in this case? They can't form common interparticle forces. Right. They can't form common interparticle forces. They're too dissimilar. Hydrogen bonds are not at all like dispersion forces. You can stand there and shake till the cows come home and nothing's going to happen. That sucrose just falls to the bottom of the tube and it stays there, and you stop shaking and it's still blocked down there in the bottom of the tube. Not a bit of it going in the solution. Alright? Now, what if we took something like sodium chloride? Alright, what kind of a substance is that? Well, it's an ionic compound, right? So what kind of interparticle forces do we find at play in solid sodium chloride? Ionic bonds, right. Now, mix them together. Take some liquid toluene, throw in some solid sodium chloride, start shaking away. Are you going to get a solution?
No.
You are not. That is correct. Why not?
They can't form interparticle forces.
They cannot form common interparticle forces. That's right. Ionic bonds are too dissimilar from dispersion forces and nothing's going to happen. Now, isn't that simple? Isn't it? Heavens yes. Alright, look at the sheet. We've got all these various and sundry examples explained there. So, go from there, and you shouldn't have any trouble then solving out any little solubility issues that we might present for your consideration next Wednesday. Should you? Heavens, no. Alright, so I think that pretty well takes care of our solubility stuff. We've talked about all of that. And so now let's get to chemical reactions. Alright, now what is a reaction? Well, reactions result when one of two things happen. You bring together substances and you either form chemical bonds between them, or you break chemical bonds. That's what's going to happen. So whenever you've got a chemical change or chemical reaction take place, what is happening is either bonds are being formed or bonds are being broken. Alright? That's all there is to it. You either form bonds or you break bonds. One or the other. Alright. Reactions can then be organized into general types by looking at the nature of the reactants and products. So there's a couple more terms coming to add to your lexicon, and it's really very simple. Reactants are the substances with which you begin. Those are the things you're going to bring together. Products, that's what you get after the reaction has taken place. That's what results from it. Alright? So reactants are the starting materials, the things you bring together. And the products are the things that you end up with. They're what result when the chemical change takes place. And the way a chemical reaction is written is in this left to right form of reactants to the left of the arrow, products over on the right. Okay? Alright, now it's always that typical way of looking at it, and so we're thinking of reactants yielding products. In fact, some people will say, read the arrow as the word yield. So reactants yield products. All right, now that's pretty simple, is it not? All right, so now if we go on, let's take a look at the first type of general reaction, which is called either a combination or composition reaction. All right, here's the general form. A plus B yields AB. All right, now just a few little tidbits here. All right, A and B are the reactants. That's what's going to be brought together. And if they react, and they would in this case, they give us AB, which is a product. How many products did you get this time? How many reactants did you start with?
2.
At least 2. All right. Typically now, AB has to be a compound. Has to be. All right? A and B, they might be elements, they might be compounds. But anyway, AB is a compound. All right? So there's a single product, which is a compound. All right, let's look at an example. Here's a specific example of a combination reaction. What are our reactants this time? What is this? What's this element? Potassium, right. And what is this? Chlorine. Ah, not yet. Because Cl sub 2, why? Why is it written as the sub 2? Diatomic molecule, right? That's the way chlorine comes as an element. See, it's uncombined with anything else there on that left side. All right, what have we got over here? We have potassium chloride, right? Now, what about those 2s and everything? Well, you know, the thing of it is, this has to be balanced out. All right? We can't take anything but 2 atoms of chlorine here. That's the way it comes. So, potassium is plus 1, chloride is minus 1. Over here, we've got to have 2 potassiums with it. In other words, we've got to have equal numbers of atoms of every element on both sides of the equation. That's why it's written that way. That's why it's balanced. And here we have a coefficient written in front of, you know, we don't go messing with subscripts because then we're changing the identity of things. Hands over this thing. All right, now. All right, so there it is. Now, this is also a redox reaction. Now, what on earth is that? Well, redox is just simply a contraction of reduction, oxidation. Now, there's some terms from the past. Reduction and oxidation. All right? What do we mean by oxidation? That's probably the simplest one to start with. How would you define that? Losing what? Electrons, right. What's reduction? Gain of electrons, that's right. So what was oxidized and what was reduced? Well, that's easy to figure out. All right, let's do this. Let's write this over on the board and we'll play around with it a little bit. All right, so up we go. All right, so I've got potassium and chlorine, and I end up with potassium chloride. Now, what is the charge over here on the left of this potassium? Tricked ya. Potassium, the element. See, it's uncombined with anything else. Right? So what's the charge on an element? What's an element made of? Neutral atoms. That's right. So what's the charge? Zip. Alright? Now, what's the charge on the chlorine over here on the left? 0. Correct. It's uncombined with anything else. Alright? These are both elements over here. Now, over here, what we have the potassium ion. What's the charge on it? +1, isn't it? What's the charge on the chloride ion? -1, is it not? Okay? Now, how did you get from 0 to +1? Did you gain or lose electrons in order to do that? If you gain, you're going to go to a negative charge, aren't you? See? All right. Lost electrons. Now, what do we call that process? Loss of electrons. What's the term? How do we define it? Oxidation, right? So we would say the potassium was oxidized because it lost electrons. Now, chlorine goes from 0 to a negative 1. How do you get from 0 to a negative charge? Gain what? Gain electrons. Right. All right, what is the term that means the gain of electrons? Reduction. The chlorine was reduced. That's correct. So why is that a redox reaction? Because something was oxidized and something was reduced. What was oxidized in this case? Potassium. What was reduced? Chlorine. Right. All right, well that's simple, isn't it? Why is this a combination reaction? How many reactants? How many products? Get a single product, it's a combination reaction. All right? Now, here is another example of a combination reaction, and this is one that is a non-redox example. And this is something that you do all the time, even though you don't think about it. What are our reactants this time? Water and carbon dioxide. That's right. The product is something we would call carbonic acid. And every time you go bubbling CO2 through water, you're going to make it. All right? That's also a combination reaction, is it not? Why? Two reactants, a single product. This one would turn out to be non-redox because nothing was really oxidized and nothing reduced. If you go back and chase down all the charges, they haven't changed. Now, we're not going to bother with that. But most of the time, these things tend to be redox reactions if they're combination reactions, okay? There are a few exceptions to it, but generally speaking, a lot of times they are. Okay, now, let's move on to the next topic. All right, we've talked about that. We know what oxidation and reduction are, so let's just keep moving. Come on, we go. Decomposition is the next general type. Now, what about that? Well, this is like turning the train around and going the other way. AB yields A plus B. Well, now, what would AB have to be? An element or a compound? It's a compound. How many reactants are there this time? One. How many products? At least two. All right? At least two. All right, here's a reaction that is an example of that. Whoops. All right, well, that's all right. I put that up there, couldn't I? All right, now what have we done here? Here we've decomposed water. All right, water is a compound. Back to its elements, from which it's made, hydrogen and oxygen. Those are elements. All right, is this redox, I wonder? Well, what's the charge on the hydrogen here? 0, isn't it? Because it's hydrogen, the element. What is it on oxygen here? Yes. Over here, the hydrogen would have been +1, the oxygen a -2. Did they change? Yes, they did. So therefore, how would you classify this? It's a redox reaction. It is, indeed. Okay? Now, that's pretty simple, isn't it? All right? Why is this decomposition? You're starting with a single reactant, you're breaking it down into several products. Right. Okay? So we're going, in this case, from a compound to a couple of elements. All right? There you go. That's all there is to it. That was pretty simple. All right, so what are the hallmarks when you've got a combination reaction? 2 reactants at least. How many products? One. If you're doing decomposition, how many reactants? How many products? At least 2. Okay, there you go. That should be easy, shouldn't it? All right. Well, let's kick it up another notch. All right, so now let's go to what's called a single replacement reaction. Single replacement. All right, now what's the general format for this? AX plus B yields BX plus A. All right, now essentially here's what you've got. AX, element or compound? Compound, right. B, element. What's happening here? Well, in essence, what's moving? It's the cation is being kicked out and replaced by an element, right? In this case, in a compound, the cation is being replaced by an element. Okay, the element takes its place. All right, there you go. All right, let's look at a specific example and we'll probably make more sense. All right, now here is HCl, which is actually hydrochloric acid, it's in solution, and the element zinc. Now, what's happening here? Zinc is kicking the hydrogen out of the compound and taking its place. So the anion chloride shows up as chloride on both sides. But what's happened, zinc has now become a cation over here, and hydrogen is now an element. All right? So, in other words, it's like the zinc is replacing the hydrogen. That's what's happening. All right? The zinc is replacing the hydrogen from the compound. All right? Now, is it redox? Yes. I don't think there's any of these that are not. Can't think of a single case where they would not be redox, because the charge is obviously changing. Hydrogen is going essentially from +1 to 0. Zinc is going from 0 to +2 as you go across there. So those are all really going to be redox type reactions. Okay? Can't think of a case really where they wouldn't be. All right, now that is a single replacement. So really what's happening? There's an element replacing a cation in a compound. That's really what's happening. Okay? That's it. All right, that's pretty simple. So, when you see that one coming down the street as raw as life and twice as natural, it's easy to figure out. It's just a single replacement reaction. Whoops, oh, I hit the wrong remote. Forgive me. That's what you get when you have more than one. All right, now let's see here. All right, double replacement. Here's the format for that. AX plus BY gives us AY plus BX. Now, simplest way to describe this. Reactants are two compounds, right? What happens? The two compounds exchange cations. All right? The two compounds, which are the reactants, exchange cations. All right? Now, let's take a look at a specific example. All right, here we have silver nitrate. That's our one reactant, and sodium chloride is the other. These are both compounds, I think we would agree. All right, silver, when we get over to the other side, is now paired up with which anion? Chloride. And sodium is now with nitrate. All right? So really what's happened? The two compounds have exchanged cations. All right? Silver is now with chloride. Sodium is now with nitrate. There it is. All right? And these, well, they're going to be non-redox because really nothing's changing as far as oxidation or reduction. There's no gain or loss of any electrons this time. Okay? Now that's pretty simple, isn't it? Heavens yes. All right, so there we go. Now, another little wrinkle for the prune. Acids, bases, and salts. All right. Very simple. Acids, bases, and salts are all categorized as electrolytes. What, pray thee tell, is that? Well, an electrolyte is a substance that, when in solution or in the liquid state, will conduct an electrical current. All right? An electrolyte is a substance which, when it's either in solution or in the liquid state, will conduct an electrical current. Okay? That's an electrolyte. Acids, bases, and salts are all electrolytes. Okay? You have a solution or in the liquid state, you pass a current through it, it conducts very nicely usually. Alright, strong electrolytes conduct obviously more current than weak electrolytes. And we can have strong and weak. Alright, so there we go. Now, we already defined that, so what's an acid? Well, acids dissociate in aqueous solution and give us protons, or hydrogen ions if you prefer. And in fact, the classic definition for an acid is that it acts as a proton donor. It will give up protons when you put it in aqueous solution. And we're talking about aqueous solution. What do we say that word aqueous means? Water. Water is the salt. That's right. Alright, so an acid is a proton donor. It's going to give up hydrogen ions, in other words. Alright? Acid solutions have high hydrogen ion concentrations. Strong acids have higher hydrogen ion concentrations than weak acids. So a strong acid produces a lot of protons, a weak acid produces very few, comparatively speaking. Okay? Alright, pretty simple. Alright, so, just as we said, strong acids give you a lot of protons, weak acids give you a smaller number, much less. Acidity is indicated by a pH, the pH scale, and a low pH means an acid. Now, on the pH scale, here's how you calculate pH, and it's very easy, and don't go into heart failure over that formula. pH is the negative logarithm of the hydrogen ion concentration of a solution. Now, what's a logarithm? It's an exponent. It's an exponent. That's all it is. That's all it is. Alright, here's the pH scale. It's a 0 to 14 scale. So the pH scale is a 0 to 14 scale. 7, smack dab in the middle, is neutral. It's not an acid, it's not a base, in other words, okay? If you go below 7, you have an acid. Acids are going to be below 7 on the pH scale. Alright, so if something has a pH of 5.4, it's an acid, right? It's less than 7. If it's greater than 7, then it's something that's a base or it's alkaline. Alright? So, if you were to take the pH of a soapy solution, you'd probably find that it's probably up around a 8 or a 9, something like that. Alright, it's alkaline. Alright, there we go. 7's in the middle, that's neutral. You go below 7, you're looking at something that's acidic. You go above 7, it's something alkaline. The lower the number, the more hydrogen ions you got. So in other words, if you've got one thing that's got a pH of 2 and something else that has a pH of 3, which is more acidic? The pH of 2. That's right. Okay? Now, high hydrogen ion concentrations give you, as we said, a low pH. Because a strong acid produces a lot of hydrogen ions, that's going to translate into a low pH value. Alright? And if you don't have a very high hydrogen ion concentration, well, that gives you a higher pH value. Okay? So, there we go. Now, bases. Well, in aqueous solution, they act as proton acceptors. Oh, do you see this? You see how, like oxidation reduction, you have either electrons lost and something else gains them? Well, what happens here? Acids donate protons, bases accept them. Okay? That's the difference. Protons can come from water. Alright? So what do you generate when you have a base? You put it in aqueous solution, you get a lot of these. Now, the OH with a -1 charge, that is a hydroxide anion. And I don't think that was on our list. Shame on me, probably should have been. It's spelled Hydroxide. I'll write it up here when I put the screen up in a minute. Hydroxide. Alright? So when you have a base, you're going to have hydroxide ions generated. Alright? Not many hydrogen ions, but a lot of hydroxide ions. Alright? That goes along with the base. The stronger the base, the stronger the concentration of hydroxide ions. Alright? And the more hydroxides you got, the higher the pH is going to be. Because remember, when we're talking about a base, where were we on the pH scale? Above 7, right. Alright, and the weaker it is, of course, the less hydroxides you got. Same kind of deal. Stronger bases give you more hydroxides, weaker bases give you fewer ones. Okay? Alright, now, another wrinkle for the prune. This is the pH. This thing just basically shows different things at pH, different pHs. So I would be concerned about that. Here's the next thing we do want to be concerned with, and that's what are called salts. Now you already know what they are, even though we never called them that yet. Ionic compounds are salts. Ionic compounds are salts. Now, why? Here is the prim and proper definition of a salt. A salt is the neutralization product of an acid and a base. If you mix together an acid and a base, you end up getting a salt as your end product. And salts, as we said, are ionic compounds. So ionic compounds are salts. And you can easily figure out which acid and base you have to react together. I'll show you an example just for the kids. I don't think we need to worry too much about it, though. All right, now here's an example of a reaction, a neutralization reaction, to form a salt. Now, first of all, we can call this neutralization because what are we reacting? We're reacting an acid and a base. But when you go back to those basic types of reactions that we looked at a little while ago, what other type could you use for this? How else could you have classified it? Huh? All right. Compound or element? Ah, bless you. That's a compound, that's a compound. They kind of exchange cation. It's a double replacement reaction, is really what it is. Alright? Now, what have we got? Here's an acid. Here's a base. They exchange cations, and what do you end up with? There's the salt, and you get water as well. Alright? So there it is, a salt and water. Sodium chloride's a salt, right? Why? Neutralization product of an acid and base. What kind of a compound is it? Ionic or covalent? Yes, it's ionic. Salts are ionic compounds. Any ionic compound is essentially a salt. Doesn't that neat? Yes. Now, there we said that. Alright, well, you can take a look at that stuff, but I've got something else to give you that isn't in the outline. Okay, there we go. Go ahead and shut that off. And that something is acid list because I think we have some acids that we ought to know the formula for. And so we will conclude with those. Let me get my little list here. Oh yes, you'll find this quite stimulating. I know. Oh, here we go. In fact, it's a good measure, you've got some bases to throw in with it too. All right, for acids. All right, so HCl, that is hydrochloric acid. All right. H2SO4 is sulfuric acid. All right. H3PO4, that's phosphoric acid. And you probably can notice there, the naming conventions here. All right, HC2H3O2 acetic acid. And a weak solution of acetic acid is vinegar. And here's one we had up a while ago, H2CO3, that was carbonic acid. And then finally, HNO3 is another biggie that you see a lot, nitric acid. All right, so there we go. So we have hydrochloric, sulfuric, phosphoric, acetic, carbonic, nitric. Those are the ones you really need to know the formulas for because we use those a lot. Now, here are some bases. All right, first of all, ammonia gas, but it's usually when it's in water, it's in the form of ammonium hydroxide. Okay, that HYDROXID. The OH minus one is a hydroxide. All right, sodium hydroxide is a very strong base. And is potassium hydroxide. You don't want to stick your hands down in a solution of that stuff, I'll tell you. All right, so there you go. All right, so there's a nice little acid and base list for you. Now, just for kicks, let's put a couple of those together and see what we get as a result. All right, so we got a minute left. Let's put together, oh, I don't know. Let's have, okay. All right, so there we are. We've got acetic acid and potassium hydroxide. If I put those two together, what salt am I going to get? Now remember, it's changed cations. So take this hydrogen and stick it over here. Take that potassium and stick it over there. So what salt are you going to get? Yes. KC2H3O2, and what would be the name of that salt? Potassium acetate. That's right. That's right. Potassium acetate. And if you have HOH, well, that's the same as saying H2O. That's water. So there you go. All right? So if you put those two together, you'd end up with potassium acetate. Now, in the salt, which ion came from the acid? Was it the cation or the anion? From the acid. Which one came from the base? The cation came from the base. Alright? Now that's simple, isn't it? Now, one more little wrinkle. I know we're about out of time, but I'm going to do it anyway. Alright, let's suppose I have that salt. What would be the name of that?
Sodium sulfate.
No, H. Sodium sulfate. Alright, now, if that came from the base, what was the base? Well, now all you got to do, throw hydroxide on it. We got it done. Alright, and if that came from the acid, all you got to do is throw on however many hydrogens it takes to get a neutral compound, right? So the sulfate would come from sulfuric acid. All you got to do is throw a couple of hydrogens on it, you got it done. Now that'd be easy, wouldn't it? I don't think I'm going to ask you to do that. But we ought to know what an acid, a base, and a salt are by definition, right? And we ought to be able to pick them out when we see them coming down the street as broad as life and twice as natural, don't you? Next time we're going to talk about organic compounds. And then Wednesday we'll be ready for a little written exercise. So there is a couple of organic compound practice sheets. You might want to print those off, bring them with you next time as well. And we'll spend a little time with those. We'll be in good shape. All right, very good.